Okay, we continue to learn Chapter 3, Vector Space. Section 3, Linear Independence. Part 3, Linear Dependence and Singularity. We will find the relation between linear dependence and singularity. Okay, first we see this theorem. Theorem 3.3.1. Let A1, A2 till An be n vectors in Rn, and let A be composed by these n column vectors. The vectors A1, A2 till An will be linearly dependent if and only if A is singular. We prove this. Okay, this equation C1 times A1, the first column A1, plus C2 times the second column of A2, plus till plus Cn times the last column An. You can write this linear combination as this matrix A times a column vector C1, C2 till Cn. So this column vector is composed by the coefficients here. And this one equals A times C equals 0. Has a non-trivial solution if and only if A is singular. Right? Thus A1, A2 till An will be linearly dependent if and only if A is singular. And this theorem tells us that let A1, A2 till An be n vectors in Rn, and let A be composed by these n column vectors. The vectors A1, A2 till An will be linearly independent if and only if A is non-singular. This one just comes from the previous one. Okay, we change linearly dependent by linearly independent here and singular by non-singular here. Okay, how to check whether a series of given vectors they are linearly dependent or not? So we use this way. To test whether n vectors A1, A2 till An in Rn are linearly independent or dependent, we first form this matrix A. A be composed by A1, A2 till An. This is a square matrix. And we check if A is non-singular or singular. And we do the Gaussian elimination on AC equals 0 and check to see if there are free variables. If there are free variables, then they are linearly dependent. Otherwise, they are linearly independent. Or you can compute determinant of A. We know that determinant of A equals 0 if and only if A is singular. So if A is singular, then this means these n column vectors, they are linearly dependent. If you compute determinant of A does not equal to 0, this means the column vectors, they are linearly independent. Okay. We check this example. Ask you to determine whether the vectors 4, 2, 3, 2, 3, 1, 2, minus 5, 3 are linearly dependent. So you can form it as a matrix, square matrix A, 3 by 3 matrix. And then you compute its determinant. You can find this one, for example, using Gaussian elimination, you find that the determinant equals 0. The vectors are linearly dependent then. Right? Using the determinant for this matrix requires that you have a n-dimensional vector and you have n vectors. So it's a square matrix. You can compute its determinant. Otherwise, you need to use the definition of linearly independent or linearly dependent to check whether this series of vectors, they are linearly dependent or not. So the general way should be C1 times A1 plus C2 times A2 plus till plus, for example, Cn times An equals 0 to check whether there are trivial solution, non-trivial solution or not. Okay. Now, to test whether k vectors A1, A2 till Ak in Rn, where k smaller than n, are linearly independent or linearly dependent. In this case, we cannot use determinant of A because only square matrix can use determinant, can have determinant. And rewrite C1 A1 plus C2 A2 plus TL plus CK AK equals 0 as an overdetermined system AC equals 0, where A equals A1 A2 TL AK. and check if AC equals 0 has free variables. If it has free variables, then these vectors are linearly dependent. Otherwise, they are linearly independent. Okay. It will have non-trivial solutions if and only if the row echelon form of A involves free variables, right? And if there are non-trivial solutions, then there are free variables. The vectors are linearly dependent. Okay. If there are no non-trivial solutions, no free variables, then C equals 0 is the only solution. Then the vectors are linearly independent, corresponding to the definition of linearly independence. Okay, see this example. Ask you to check whether x1, x2, x3 are linearly independent or not. The general way is you write them as the system equals 0, the linear combination of these given three vectors equals 0, and then you solve the homogeneous linear system, right? Should be C1 times x1 plus C2 times x2 plus C3 times x3 equals 0. And this linear system you can write as a matrix 1, minus 1, 2, 3, the first column, the second column, minus 2, 3, 1, minus 2, the third column is 1, 0, 7, 7, times C1, C2, C3, times this unknown vector equals 0, 0, 0, 0, right? And it is equivalent to solve this system. You write the augmented matrix, and then you use the Gaussian elimination to transform it to row echelon form. And when you write it here, you will find there's a free variable, right? The echelon form involves a free variable C3. There are non-trivial solutions, and hence the three vectors, they are linearly dependent. If there's non-trivial solution, linearly dependent. Okay. Now we consider the equivalent characterizations for non-singular matrices. So let A be composed by n column vectors, A1, A2 till An. Here it is n by n square matrix. The following are equivalent. A is non-singular. This one is equivalent to B. Ax equals 0 has only the trivial solution 0, has only the 0 solution. And which is equivalent to the null space of A equals the 0 vector only. And C, this one is also equivalent to Ax equals B, has a unique solution, x equals A inverse times B. And also equivalent to this one, D, A is a row equivalent to I. And E, determinant of A does not equal to 0. And here, F, you have another equivalent characterization for A is non-singular. If and only if F holds, that is A1, A2 till An are linearly independent. Okay. Now we consider the uniqueness of a linear combination. We have this theorem. Let V1, V2 till Vn be vectors in a vector space V. A vector V in span of V1, V2 till Vn can be written uniquely as a linear combination of V1, V2 till Vn if and only if the given vectors V1, V2 till Vn are linearly independent. Okay, so if for any vector V in the space capital V, the expression of a linear combination of the given vectors is unique, then we can say these given vectors are linearly independent. The proof is easy to follow. So if it can be written as a linear combination of uniquely as a linear combination of V1, V2 till Vn, this means none of the Vi's can be written as a linear combination of the others. So the Vi's must be linearly independent.